something around myself, about myself. I finished my education in 1995. Let's say last century, previous century, and actually I finished it. At those times there was only one university. Where the education of chemical engineers was possible. It was just AZI. We call this AZI, Azerbaijan University of Chemistry and Oil. Right now, if I'm not mistaken, it's just Azerbaijani Technical Oil University or something like this. Because at the time when I was finishing the university, when I was completing my study, it was just Azerbaijan Oil Academy. Name was changed several times after this, I believe. On completion of my study, I started working in oil field, Binagedi Neft, and later on moved to the Balakhan Neft. Later on moved to the one joint venture called Asger Neft. After the Asger Neft, I moved to the oil refinery, named after the Heydar Aliyev. I used to work on the crude oil distillation units and the catalyst cracker unit. Also, when I worked for quite extensive time over there, around 9 years over there, and later on I've changed my working place to BP. Started working as an operator in the West Azeri platform, and from 2008 I started working as a process engineer in engineering team. Majority of the time when I was working in BP, I covered mostly offshore platforms, but for the last 2-3 years, I'm supporting midstream operations, mainly in Sangachal terminal, with some very intermittent works carried out on the pipelines. The reason why I choose the pump topic, it's mainly because I know that just you are extensively taught some kind of things like hydraulics around the pumps calculations and PSH calculations. I will not be giving a lot of calculations in my presentation, because I know that just majority of this you know already, or you will be know by the end of your course. But again, main reason was just during the interviews. I'm participating a lot of interviews carried out for the summer interns and also for the professional engineers, not all of them, but some of them, and a lot of questions around the pumps asked, and I know that just majority of people cannot respond to this question. And I would like to share something which I know and which I ask usually in interviews, and I know that just some people and other people also ask. I really hope that it will be very valuable and very useful for you. It will be interesting for you as well. And will not be going to the hydraulic stuff, just only purely about pumps. Another thing, just why I would like to mention about the pumps, you know, process engineering now includes majority chemical engineering people, includes general chemical engineering team, but it wasn't like this historically. Historically, process engineers used to be mechanical engineers, taken from mechanical engineering, where in the beginning of 70s, they decided that just, okay, chemical engineers are more appropriate for the process engineering work rather than mechanical engineering. Main reason was just understanding the process parameters, chemistry, physical change of materials, stuff like this. Even now, a lot of work which have been done by mechanical engineers or rotating engineers requires involvement of process engineers which have got process engineering background. And you will be very surprised when you see that just any equipment on the site, when it's designed, it starts from the process engineer providing the process data. And process engineer can, in this alone, can design majority of the equipment which is installed on the plant. I'm not minimizing the value of mechanical instrument control and electrical engineers, but I would like to, their knowledge is also required. They've got some deeper knowledge, but I would like to emphasize the meaning of process engineering in designing, in identifying, or just of this kind of equipment. It's not only pumps, it's compressors, valves, separators, internal of separators, a lot of things. Just I would like to go to the next slide about what is a pump generally. I will not take a lot of time for this kind of for this slide. There is enormous amount of definition in a available, let's say. Actually, I like old Soviet definition, and actually I found in Britannica have got similar definition. Pump is a device that extends energy in order to raise, transport, or compress the fluids. Generally, pumps are just applicable to any fluids. Doesn't matter is it liquid or gas or solids, but historically, it was just all around the pump. Pumps are used only for the moving the fluids, like liquids in the systems. Just as a pump, as a device, as a pump, it have got very big history. Actually, it started maybe 2,000 or 3,000, thousand years ago, and pumps were available during the Archimede time. And historic in ancient Persia, there was windmills pumping the water from one side to another one for the watering the plants. Islamic era, just in 10th, 30th century, they had pumps, and actually initial understanding of some physical, how they say, physical phenomena, something like pressure, was just identified during the Islamic countries of the 10th or 13th century. The main was just pressure. There is some known stuff just as a Cairo water tower or Madrid water tower, which was built in ancient times. Another thing, just there was some point, there is some kind of pumps used in China and Japan, and very big investigation carried out in 17th century in Europe and during in the mining and civil works, and identification for one atmosphere started from the developing the pumps. For example, there was just a manual reciprocating pump developed, and maximum the pressure, which can maximum the water height which it could suck from the mine, it was just 10 meters, which was equal to the 1 atmosphere initially. Later on, it was just some definition of bar was generated. This is something like historical. You can find this in internet, in Wikipedia, a lot of background around this one. General classification of the pump. The pumps generally classified in three methods. Mainly, it's just how energy is provided to the liquid. One of them is volumetric displacement. Another one is by addition of kinetic energy. And third one is use of electromagnetic force. It's for the ionized liquids. We will not be discussing this third method because I've got limited knowledge, and actually it's very specific stuff. Before going to the type of the pumps, for the detailed all first two methods of energy provided, I would like to show you just pump selection chart. It shows it's dependent on head and capacity. And actually, this is main stuff because during the interviews, I'm asking how you would choose, me personally, I'm asking that how would you choose a pump, what type of pump need to be installed. Each company, each technical book, because pump selection is not very easy. There is so many factors affecting the pump selection. It's usually not very easy. But this is just something like as a startup for the pump selection and pump system design. This is pump chart. Again, different companies, different books providing the different charts. And from this chart, you will see that just for the higher flow and lower pressures, usual centrifugal are used. And for the higher head, but lower flows, just multi-cylinder plunger, positive displacement pumps are used. But this is not must, because I know that just a lot of centrifugal pump which operates at the high head and low flow sections, and backwards there is a lot of positive displacement pumps which are running at the low head but high flow. This is special cases. It's not standard cases. There is some selection carried out from the companies themselves. So it's just this is just something like willing of the companies who are installing the pump. But generally, these charts are perfect for the initial identifying what pump would you like to use. Now I would like to go a little bit about the pump type of pumps. By the way, Rashad, I would like to ask how would just identify, are there any questions in the chat section? And who will be just providing?
In the chat section, if there is any question, it will pop up. And currently there is no question. And if there is a question, I will notify you.
Okay, okay.
All right.
So generally, we will be discussing only two types of pumps: volumetric displacement and dynamic pumps. Volumetric displacement, where the liquid physically displaced mechanically or by another liquid, fluid, not only liquid. There is several types of them. Generally, they are divided into subgroups: positive displacement, reciprocating, and rotary. Reciprocating is just physically when the how they say, piston is displacing the liquid. It can be divided to piston, plunger, and diaphragm type of pumps. And there is another type, subtype of rotary, which is screw, gear, sliding vane. There is many of them. I will not be going to the detail how they are designed, how they are constructed, what's their specific, but actually we'll speak the main thing about these pumps. And in the same time, dynamic valves, dynamic pumps can just where kinetic energy is added by either by rotating at high speed or by providing impulse in the direction of the flow. There is three types of the main type of the valves. One of them centrifugal, which includes radial flow, axial flow, and mixed flow, and many others as well. It's not limited to this one. And peripheral regenerative turbine. There is very limited use of these peripheral pipes. Usually it can be as positive displacement pumps because they're generating quite high head and very small flows. But actually their use is very limited, so you will not be finding a lot of stuff around, and they are not very widely used. And last one is jet pump. Jet pump sometimes is divided as a third type of the pumps. And I will be giving some tips around jet pumps. Will not be touching too deep, but actually I will be giving some information about these pumps as well. When you are starting designing the pump, the first things just coming to you should be coming, and actually the easiest choice is just centrifugal pumps. They're quite robust. They're very widely available. They can be designed in very various how they say, they can be applied to the high pressures. They can apply it to the small flows. There are high-speed pumps, low-speed pumps. Any type of centrifugal pumps are available in the market you can use, and it's beauty of the centrifugal pumps that they are very well known and very well designed. There is a lot of knowledge behind these pumps. let's say, for example, there is some high-speed centrifugal pumps located on which is running with very low MPSH, and there is, especially in Azerbaijan, currently it's changing, but actually previously there was water injection pumps installed on DWG platforms. In Azerbaijan was the biggest in the world. 3 is the biggest centrifugal pumps installed in the world. Not only in the size, but actually in terms of the pressure, because it was just used for water injection into the reservoir, and in terms of the volume as well. And you can imagine it was in volume, it was just as big as, let's say, water pumps, which provides water to the Baku city, or just to the, not only Baku city, but to the biggest city, like New York and London. It was just quite enormous pumps. And just as I said, just first thing, which we are starting designing the pumping system is just centrifugal pump. And what you should be consider when you're designing an NPSH, pump differential pressure, and system resistance curve. Everything starts from the system resistance curve. This is quite big topic, system resistance curve, and actually I would like to check what's okay, I've got 3 questions I would like to answer to them. First, what parameters does the total head depend on that chart? Its head is just energy provided by impeller, or just by, it doesn't depend on any other except of the power, even not power. It's just definition of the energy which provided by your pump to the fluid. So it doesn't matter of the temperature, it doesn't matter. It's depend on viscosity, but actually I will be coming to this in my presentation. Generally, head is not depending on temperature and viscosity, but actually pump performance and pump head provided by pump can be affected by various process parameters. Would rather say mainly from discharge and suction pressure. I would say differential pressure across the pump, because pumps are just liquid. It's not something like, it's like a different from the compressors, from the gas. Liquid quite stable. Again, I will discuss some kind of things, and if you give me more detailed questions, and I will just explain it better. Generally, for this chart, which I had before, the heads are in the meter of water, not even liquid, and capacity is a meter of cubic meters per hour. And pressure is just for, how would I say, again, pressure generated by volume, by the height of the water rather than hydrocarbons. It is calculated, pressure is calculated from the head, recalculated, and I will come to this. And you can ask additional questions as well, there is no problem. I tried to answer to your questions, but actually I might be not answering to your questions. If it's not clear or it's not appropriate, just please write it down again or just ask me straight away. And when you are starting designing, you should start from the system resistance curve. Just what head do you need? For example, differential pressure head, what head do you need to pump liquid from one separator to another separator, from one equipment to another equipment? What's the distance between them? You are putting the line, you choose the place where you put the pump, and you need to start putting the, and actually when you are putting the line, you will see what's the system resistance on the pump. How much head do you need to pump this liquid from one point to another point? And actually, the curve is dependent on what flow are you are putting. For example, at 10 cubic meters, it can be doing that. For example, head of 20 meters are required, and 100 you need something like 25 meters required, and you are putting this curve, and according to this curve, you are starting designing the pump. Unfortunately, I don't have all my information, all my books, all my notes, papers are just left in the office, and I just use everything which is in this presentation I took from internet. And to be honest, internet is not a very great place to get this. It is a great place, but actually I was struggling to get the information which I wanted to share with you. So, but actually some of them will be appearing in this presentation. For centrifugal pump, this is main curve which I've got, and actually every time during the interview we were asking, please draw me the pump curve for centrifugal pump, and this is head towards the capacity, and this is a curve which called H, which under the H. This is a curve of the pump and indicating at what capacity, flow capacity, what head is generating. Again, I would like to inform, because it's traditional stuff. It's something like scientific. Traditionally, pumps were designed. All formulas was referring for the water, and when the pump design is completed, the pumps are usually tested on the factory, and factory is the widest available and most easy liquid is the water. So all curves which you can see in the pump manufacturer or all of them are based on the water. And what you will see in the centrifugal pump curve is generally power curve. Sometimes it goes down after some point. It's a head curve, efficiency curve, and NPSH curve. There should be another just I will come to this a little bit later. And I would like to inform that just main disadvantage of centrifugal pump, they're not very efficient. I don't think that they're inefficient. They're efficient something around normally 75–80%. Very rarely it's something like 65, and very rarely it comes up to 85%. But actually it's quite really rare. And that's just what you was asking, head. From the head, we can calculate the pressure which can pump generate. And actually, this formula, I pretty much sure that you know this formula as well, Roger Hash. And actually, pump differential pressure will be equal to the density, as one guy was asking, and head. Density is at the temperature of liquid at which liquid is being pumped. So temperature, of course, temperature depends on the density depends on the temperature, but actually, if you're asking me what temperature can affect the pump discharge pressure, it mainly affects the density, and that's why it affects the pressure, differential pressure as well. But head just stays the same. Now I just would like to go to the, let me check 2 presentations. Recently I was asked how to start, not recently, I wasn't asked, just we was discussing with another process engineer, how is correctly, properly right to start and operate the pump. On the pump curve, you will notice a lot of enormous information. And actually, just let me go a little bit back for the NPSH. One of the main stuff is just NPSH required. At the NPSH, when the NPSH required, it's a head required for pump for proper operation, mainly to prevent cavitation. At the point at the end of the curve, on the right side curve, some liquids can be at the point where the liquid comes to the vapor pressure, and it might be, and a pump can face cavitation. And in pump curve, you will find some preferred operating range and best efficiency point somewhere around this point. Why is the preferred operating range is matters? Because there is allowable operating range and preferred operating range. What's the difference between allowed and preferred? Allowed operating range is just place where the low flow cavitation starts. And at this point, you are not allowed to operate the pump because it will be damaged through the cavitation. And this cavitation appears due to inefficiency of the pump. Yeah. If you remember efficiency curve, there is efficiency drops down at some point of the head. And for example, if it's efficient for 50% or for 55%, less 40, 45, 50% is changing to the heat within the pump. And this brings vapor pressure of the liquid, which is being pumped to be high, and liquid starts boiling and cavitating. The head generated by pump start pulsating because when it sees the liquid, and easily be damaged. Another point is just, and in the area between the allowable operating range and preferred operating range, there is several points are located. Let me check what kind of questions we have got in the chat. Okay, I will answer to high viscosity oil as well. Thanks, Mehdi. I will just ask this question a little bit later. Just would like to describe this curve because this curve is is used for by the process engineers very widely, very often, and that's why I would like to discuss this one as well. And for example, as you know, just all pumps, every pumps nowadays, and previously it was just refinery slightly different for the oil production side is slightly different, but actually many years ago, the pumps were operating just in one point, and recycle of the pump was just, a lot of companies was avoiding to using the recycle of the pumps, on centrifugal pumps especially, because pumps it's inefficient, and with opening pump, we are wasting a lot of energy. Nobody wants this, and especially for refiners, the refiners was purchasing the power from the outside. Majority of them, they wasn't producing the power by themselves because of very constrained liquid. Even for the generation of power, they need the fuel, and fuel was just bought from outside. And that's why there was, but actually right now, the the company starts installing the recycle valves. It becomes normal standard procedure for still some refineries are still considering not running with the recycle valves, not installing the recycle valve, but actually it's coming more and more as standard design of the pump. And when you're putting the recycle valve, it should be just installed on the minimum preferred operating range. All this figure, all the points, which is on the curve, which is low cavitation, low flow cavitation, reduced bearing and seal life, reduced impeller life, suction recirculation, discharge recirculation, it will be behind of this preferred operating range. But I would like to inform that if you put the recycle valve here, you might be using a lot of energy for waste, because your pump will be operating on recycle in a very wide range, range. So some companies are just dismissing some of these points and but they just don't exclude low flow cavitation, and they're installing the minimum flow line on low flow cavitation point. What does mean reduced bearing and seal life? If you operate the pump in this area, because of instability of the pumps, instability of operation pump, because at this point, pump impeller, pump shaft becomes unstable. As you know, just pump shaft is pushed from one side to another side. One side is connected to suction, where there's a lower pressure. Another section is connected to the discharge, where there's a higher pressure. And there is some push from the discharge to the suction. And at this point, at the reduced bearing and seal life, it becomes a little bit unstable, and shaft starts moving towards suction and discharge side, damaging the bearing and seal life. Another one is just reduced impeller life. The cavitation this is just low flow cavitation. This is a cavitation only inside on the section of the pump. What happens inside the impeller, this is a different story, and that's why they're using the point called reduced impeller life. Even if the pump is protected from low flow cavitation, at the time you will see the degradation of the pump performance, and when you are stripping the pump, you will see that some cavity in some erosion on the impeller, and damage to there is some balancing ring installed on the pump. I didn't put pictures of centrifugal pumps because I didn't want to go to the mechanical stuff, but there is some balancing ring, wear ring, they call it also wear ring, and at the reduced impeller life impeller life, this wear rings and impellers can be damaged. And suction recirculation, discharge recirculation, because it's not very, how they say, they're not tightly connected. Impeller and the casing of the pump, they don't have any tight connection with each other. There is some small gap between them, and which allows some liquid to be recycled. And this is specific specific stuff. I don't want to go to the deep to this one, but actually, if you want to avoid them, just your minimum flow should be at minimum operating range, and not in any case should be lower than low flow cavitation. This depends on company. Company can decide to sacrifice one of them and to put another thing. What about maximum operating range? It's mainly because of vibration. Vibration is slightly different phenomena, let's say, and vibration is just not only depend on the pump pumped liquid properties. Also, it's just something like dynamics as well. And but in this case, majority main input is given is being done by fluid, because as you see, I don't know, do you see my pointer? But actually, system resistance curve usually in pumps, it's coming like this. I will be coming to this point in the next presentation. It's actually coming like this. And when the system resistance curve, when NPSH available, when the difference between NPSH available and NPSH required is very small, liquid starts generating some vapors. And vapor generating creates imbalance in the impeller, and pump starts vibrating. And that's why just the operational flow on the right-hand side of the curve is also on, and there is no physical protection for this. If you, for example, lower flow, you can manage by the recycle. There is some company who restricting the flow by the orifice plate or control valve sizing, specially sized, just not pass more than this. But actually, this depends on the suction condition as well, so it's not very really efficient. Now, just to the question which was asked before, what is the viscosity and density? I think that just I touched this density, okay? Density doesn't change the head. Head will be stay the same. Pump will be generate exactly the same head, but pressure on the pump discharge will be vary from the density of the liquid. Vary from the density of liquid. For example, water, it will be just 10 meters will be 1 bar. For the oil, for example, with density of 860 kilograms per cubic meter, it will be something like 8.5 and 8.6 bar. But the head on the pump discharge will be always the same. Generally, this is more related to the special case. For example, I used to work in the oil industry mainly, and mainly in the oil production side. Actually, a lot of liquids which are were handled by pump in our case, in our area, their viscosity are not widely different from the water viscosity. They are different. I'm not saying it's exactly the same, but actually the difference is so small that main people are just ignoring the viscosity of the centrifugal pump. Which type of pump more appropriate for high viscosity liquids? I will come on the case where I will be discussing the positive displacement pump, but general for this case. And when the viscous liquid, and for offshore platforms, for midstream, there is small change for the viscosity. But for example, in refineries, so as a, for example, liquid like hydron, I don't know, do you know this kind of liquid? It's just vacuum residue is handled. Viscosity stuff is just very vital, and actually you need to make adjustment for its viscosity. And there is just there is a unit. I didn't put the formula here, but actually there is unit called mu, and actually, oh, okay, it's here. And no, it's not the same. It's simple. Coefficients for the energy, pressure, and energy, power, and head correction. There is 3 constants. And actually, these units are widely available in the chart. It just, every manufacturer will be giving this chart to you if you are asking. And actually, these liquids are very sensitive to the pump. They can be standardized between all pumps, and actually they are standardized, but actually, some companies have got some special charts. They are more robust and more robust and more accurate. And from these charts, you can find some correction factors, and you can find the viscosity stuff is just very one of the main stuff as well. For example, as a process engineer, you will be asked, I have noticed that there is some questions in the chat, but actually I would like to finish my expression, and after this I will come to the chat questions. As a process engineer, you are very constantly asked to check the efficiency of performance of the pump. This is quite often stuff. Because there is, as I said, just wear rings inside. Actually, sometimes platform or units are depend on the pumps. For example, platforms are designed for the capacity at which pumps capacity are available. Just for example, pump are 600 cubic meters. Your platform capacity is 600 cubic meters. You will not be able to produce more oil than your pump capacity. So pump capacity, pump performance is just continuously monitored. I would say just every 6 months, 7 months, every year, the pump capacity is checked. mainly on the oil pumps, main oil pumps capacity, checked in, for example, 6 months, 1 year around. And there is one thing which, for example, every time when you are doing your capacity checks, your capacity appears below the curve, slightly below the curve. And main thing, just this is mainly this is because of the coupling losses. Coupling losses is a power loss in the coupling, in the bearing, in the seal, and stuff like this. Previously, just many years ago, let's say at the 80s, it was just widely ignored, and actually later on, and just physically, pump motor capacity plus 10% was just allocated to the coupling losses, and hydraulic power from the pump was just 90% of this pump motor was evaluated as 90% of pump motor power. But later on, just say this, and actually it can be wrong, because and on the platform, when we're just assessing the pump capacity, and we're just discovering, we are seeing that just it's slightly below the existing curve, and we are saying just, okay, it's a coupling losses. But sometimes it might be wrong. This might be viscosity losses. And I many times, just for the younger engineer who came and assessing the pumps, I many times trying to push them to check this viscosity losses, head losses due to viscosity, efficiency losses, power losses due to viscosity change, and then just adjust coupling losses after this. And you can, I would say this is quite very, very, very important stuff, because, and very small stuff, you need to have something like fantasy to identify what can be viscosity losses be. For example, seawater. Many people are just saying that just it's really water, there is no big one, but actually at the time when I was looking through these seawater cases, I still insist myself to check the viscosity as well, because seawater have got some salt in it, and salt are changing the viscosity of the water. And yes, it's negligible, and actually it might be ignored, but actually this is one of cases which when I was looking, I was just looking through the viscosity of seawater and how it's different from the viscosity of water as well. There was no big difference, but I was considered. Another thing, just on one of the MEG regeneration units on the Chardonnay's platforms, there is salt precipitated in a liquid in the water. For example, MEG and produced water enters the column. MEG and water is evaporated, but on the bottom recycle flow, which is consistent mainly of MEG, there is some salt are precipitating in a fluid. Dissolved salt increasing the viscosity, but precipitated viscosity increases the viscosity dramatically. And we have got power losses, head losses, and efficiency losses because of this precipitation. And before me, nobody was just accounting for this one, but actually when I started evaluating the pumps working in this service, I started evaluating the salt, precipitating salt. It's not easy, but actually this is my suggestion, just sometimes to check the viscosity of the liquid as well. This is answer to the question, how viscosity affects the head. Viscosity affects the performance of the pump. Head is just really stays the same, but actual performance of the pump are changing. Now I'd like to go to the questions. I think there was another question up. Could explain why is the head of pump not depend on density of fluid? No. Head of the pump, again, I said traditionally pumps was designed for the water. Head is not changing, because head is generally is energy provided to by impeller. Head should stay the same, For example, the same pump will be increasing the head for the same height, but discharge pressure on the pump will be changed. I haven't been in deep on the physics about this one. If you are asking about physics, I maybe will not be able, because I finished a university around more than 26 years ago. I don't remember technical theory about this one, but actually generally pump will be providing exactly the same head, and head is just identified or evaluated as a head of water. But when you are calculating the pressure of the pump, which is generated by pump, then they will do account the density of the liquid. Density of liquid, and you will calculate, for example, again, if pump generate 10 meters of discharge pressure, for what it will be 1 bar, or the hydrocarbon with a density of 860 in kilograms per cubic meters, it will be 8.6 bar. That's Sanan, this is my question. Sorry, and I don't know the theory behind of this, if you're asking the theory, but actually I don't remember, I don't know, but actually this is what it is. Pump characteristic curve can be achieved with experimental gradual opening valve installed on the pump discharge, but don't you know how manufacturers towards the NPSH? Oh, okay, very nice question, because I've been on one of the tests for the pumps, and one of the tests of the pumps, and I can explain it to you a little bit more. I don't have picture, but I've got the graphs. I think the graphs will be more useful slightly later when I will go to the positive displacement pump stuff. Pump oil and water with the same pump, it will make the same head. Yes, it will be the same head. Head will be the same. For oil and water will be the same head. But pressure on discharge will be different. It depends on the density of the liquid. As they are already included in the system curve calculation, why there is any need to mention viscosity head? Okay. Viscosity is included. Yes, very nice question. Just yes, they are included into the system resistant curve. But actually, system resistant curve is just resistance of the pipe to the flow. But pump itself, how it will be, this is physically for the pump. Performance loss of the pump itself, from the suction nozzle to the discharge nozzle. Yes, system resistance curve will be changed, but pump performance due to viscosity change also will be changed, because the liquid should flow through the impeller, and viscosity affects the flow through the impeller as well. I hope I answered to your question. Affinity law, it's one of the main topics. Generally, I would like to go on. Let me return to this slide. Later on, just a few days ago, I was discussing with another process engineer the possibility of starting and stopping the pump with a discharge valve is closed. And generally, there is no problem. A lot of companies are doing like this, just they don't have minimum recycle flow on it, and they are just closing the discharge valve of the pump. They're starting the pump, and later on, they are opening the discharge valve. And the same during the stop. During the stop, they're closing the discharge valve and stopping the pump. But this is just really not preferable case. There is no big problem. It will not be damaging your pump, because your pump will be running only a few seconds, let's say 20, 30 seconds with a closed discharge valve, but actually you can put your pump at the low flow cavitation area. And this will reduce your pump life dramatically. So in any case, it's better to start the pump with a recycle valve open it, to adjust the flow on the preferred minimum limit of the preferred operating range, and later on start the forward flow. This is something which I came to my mind. I want to share with you this case. Let's go. I would like to go to the questions in the chat. Okay. Pump control. I would like to speak about pump control. There is 4 main methods. There is a lot of methods for the pump control, but actually 4 main methods. And so we're calculating for suction pump, not for the whole process. No, we're calculating for the pump itself. We're calculating for the whole process. We're calculating the head of the pump, and we're calculating how much will be less, how the performance of the pump due to viscosity will be slightly different, and including the system resistance curve as well. Pump are controlled in 4 basic methods. There is another one. There is enormous amount of valve control stuff. Just main one is a throttling. Throttling valve usually installed on the pump discharge, and you just can close, open it valve slightly more, slightly less. And this is most efficient. No, I'm wrong. It's not very efficient, but actually this is simple and how they say easy solution for them. In efficiency, it's better than bypassing, but actually this is better than bypassing, but actually this is again should be avoidable. This throttling is just very widely used in refineries, and actually in offshore and onshore, in upstream and midstream as well, but refineries are using the throttling very widely. And they trying to not putting the bypass valve. Right now its procedure is changing, but previously they tried to, and actually main reason is just to keep the energy. And throttling valve is just first box in the, just when you're just throttling the valve on the discharge, the system resistance curve is changing. If you see the system resistance curve, initially it was like this. It's now changing a little bit high because of differential pressure across the valve. And your pump is start operate in slightly different position, in slightly different place. Your system is doing the same stuff, but your pump are just operating in different position. It was okay because just if you are just imagine efficiency curve here, it goes to the less efficient point, and also your pump are just you are wasting the energy which requires to go to overcome the differential pressure of the valve. But throttling is still widely used. Just for the throttling, as I shown in this picture, there is level transmitters or some kind of things can be connected to the throttling of the valve. And actually, another one just bypassing of the valve. Bypassing of the valve, it's backwards. And this is also a waste of energy, but actually, again, if you, it also goes on the area where the pump is not very efficient, but actually it's for example, resistance curve, it's here, and you are just opening, putting the flow valve and changing the resistance curve. It's not correct to say the resistance curve, but let's say the suction line resistance is being changed. So bypassing is also not very efficient because you are just wasting a lot of energy across the bypass. And then bypassing is just putting some levels through the bypass line back to the suction. For the gap control is just switching on and switching off the pump and operating pump at one point, for example, here. When you need to pump out some liquid, you are just starting the pump, and when just it's finds some limit. There is a lot of disadvantages of this control as well. One of them, every time when you are starting and stopping the pump going through the whole cycles of stability of the impeller, of stuff like this, power overloading, also but actually widely used as well. And so what was the best efficient point and the best efficient method is variable speed. In market is just very available. It's quite, there is, for example, turbines are running on the, with a variable speed. There is a lot of electrical drives. It's called variable frequency drive, which changing the frequency of the electrical power, and the motor speed is changing and pump speed is changing as well. This is main control, and what it gives us in terms of pump, I would like to, and actually this is one of the main stuff which also process engineers should be aware and use, is the affinity law of the pump. This is one of the investigated and well-known stuff. So, and actually it's this not only for the, when you are checking the performance of the pump, you should take into account the speed of the pump at which it rotates currently. And another thing, and for example, for predicting of the for example, if you are going to increase the speed of the pump, you can predict what will be your curve. Another thing, just what's sometimes you need to modify the pumps. There is some kind of similar curves for the different impellers, because as you know, the pumps are just quite standard, and the companies are providing one casing with the 3 sets of the impeller, not with the with 3 possible sets, and actually you are providing your process data to them, and they're just choosing the impeller which is required for your need. But generally, affinity law is just duplicate this impeller stuff. And the easiest solution is to change the speed of the pump. In some cases, it's just too difficult. In some cases, it's possible. For example, on one of the platforms, there is pump. Actually can do this. It's just this affinity law can help you with the designing or modification of the pump as well. Another thing which I would like to mention, for example, motors, electric motors. I don't know how deep you're learning this kind of things, but actually how deep you taught this electrical motor stuff, but actually they can be stepped from the 2-pole mode to the 4-pole mode. For example, if you will looking through the alternative current pumps, their speed is just constant, but they can be changed. It can be 3000, 1500, 750, and actually you can predict, for example, if your pump is just doing something bigger than you expect, generating higher pressure, which your system pressure is just designing, and you can just speed it down. And in order to check your pump performance, and you can use affinity law. Just my first, I know that maybe you probably thought this topic, but actually I would like you to pay attention to affinity law. It's quite useful and useful in many times in your career. It will be used in many times of your career. Another thing, just which you are just facing it quite often, is a pumps design as a bypass and series. Series is just something like pump, booster pump, and suction and main pump. And actually, the main reason is just twice increase the pressure head. You can ask what is the real requirement for we can design one pump at, for example, instead of 2 single impeller pumps, we can two impeller pump, and so why we need to do this. But in some cases, for example, for there is two process parameters controlled. Suction pressure, for example. One pump is running to keep exactly the same suction pressure to not overcome NPSH, and another pump is running to cover discharge conditions, what pressure is required for the discharge line. And in this case, sometimes you need physically two pumps with physically different impellers running on different process conditions. In parallel, and in parallel is just physically for the, there is some cases when you need, for example, 100 cubic meters, and instead of putting one pump, it would be better to put two pumps running on parallel. Main reason why is it so? For flexibility of the system. For example, on oil platforms, when you are starting, the oil production is not maximum from the day one. It's, for example, it's run for prolonged time at the minimum. Instead of putting one big pump, it's better to put two pumps. One pump operation will be at the beginning of the platform life, and two pumps when it will be at maximum production. I missed the NPSH. I think I even didn't catch it in my presentation. I will just have a short discussion about NPSH, but would like to go to the chat questions as well. Can one multi-stage pump with a higher power can do the same job as two series? Yes, it's possible. Can you clarify why two pumps in series may sometimes be preferred to multi-stage pump? Okay, I will repeat it. In any case, you got it, but actually I will just repeat it as well again. For example, on oil platforms, we've got booster and mole pump. This was my first question when I started just during the design of the platforms. I said, why we need booster and mole pump, main oil pump. We can have only single pump, just put additional stages, and that's it, nothing you don't require. But they explained that mole pump are just mainly, main oil pump will be providing only discharge condition. What they will be just doing what pipeline can do. If the pressure is high, it will be reducing the speed. If the pressure is low and level is enough on your separators, it will be increasing the flow. But in terms of NPSH of the mole pump is not affected. Booster pump will be always there, and booster pump will be modulated to provide correct NPSH to the mole pump. In some cases, for the whole system, for example, booster and mole pump system, to not overcome NPSH of whole system, booster pump can be changed in some process parameters. Minimum flow can be opened, minimum flow can be controlled in so that just pressure, suction pressure on the mole pump will be steady. And the pressure changes in the pump suction will not be affecting the discharge pressure of the mole pump. This is just mainly stuff. Very rare case in refinery where I used to work. There was two pumps which can be lined in parallel and in series, and this was just water pumps and utility water pumps, and depend on what system is pumping, you can provide two pumps in series and provide more flow, or two pumps in the two pumps in parallel to provide more flow, or two pumps in series to provide higher pressure. But this is really very rare case. Another question I would like to answer, and after this go to the. Okay. NPSH, I would like to return. I didn't catch this a lot, I think. Where's my. Curve. NPSH is just what's the head required for pump to operate. But company who is just providing who is installing, they want to be sure. And there is another expression called NPSH available. Different company treat this function as much as they can, very differently. Even BP company used to change one philosophy from one to another. For example, some companies just adding to this head another 2 meters. Some companies adding 10%. Some companies adding even 15% more than NPSH. And even BP company changed this philosophy. And your available head should be above this NPSH required at any process condition, any flow. For example, for this pump, your available head should be slightly higher than required, at least 2 meters. The rule of thumb is just 2 meters, and many companies are using this one, 2 meters. And currently BP is using 10% of the NPSH required, but actually I'm not sure because it's changing so quick because I used to read the BP standards for quite a long time ago. Another topic which I would like to mention, it's a temperature rise on the pump. Sorry for formula. No formula is right, but actually, what about temperature rise? I have faced it several times when we need to check the temperature. Temperature rise in the pump discharge is mainly because of inefficiency of pump. As I said previously, for example, if your pump is efficient for 80%, 20% of energy which is generated by motor will be changed to the temperature. And why we need to check this temperature? Sometimes pump adding some temperature, and especially when it's a recycle, it can go over vapor pressure of the liquid. This is not very rare case. It might be quite a real case because especially in oil where the unstabilized oil coming from I understand that just it should be stabilized that the vapor pressure is equal to the pressure which is in suction separator. But sometimes when the recycle is turning back to the suction line and it's much hotter than the separator liquid oil because of the recycle, or just even slightly higher, it can raise the vapor pressure of the liquid and pump will be starting to irritate. Another thing just I would like to mention, we have got water injection pumps, and during the designing of the minimum flow valves for the water injection pumps minimum flow is, it's not water injection, seawater pump, which is providing the seawater to the injection for water injection. And there was one valve which installed on the recycle, as a recycle, for example. If seawater is taken from the sea, its recycle will be diverted back to the sea. But because of the platform height, it comes from the pressure of 500 bar to the negative pressure. And negative pressure is because the line is going down 30 meters down to the sea. At sea level, it will be 0, and actually at the height, it will be. And when we were specifying the process data, we just specified the seawater of temperature 6 degrees C. It's going and through the valve and discharging, and we're just keeping the same temperature of 6 degrees C. We have done correction for the negative pressure on the discharge of the valve because it's going down to the line. But even after this, we have seen cavitation of the control valve. When we was investigating, we have identified that due to inefficiency, the temperature of the water is increasing the vapor pressure of the water, which is going through the control valve and cavitating in the control valve. Another thing, just during the startup, pumps are required to run for the long time on recycle, increasing the liquid level in the suction side, and physically to evaluate how much time do we have till the time when the temperature will be becoming dangerous. You need to make a calculation of that temperature. This is quite useful stuff. Just I personally used it for 4 or 5 times in my life, and actually this is a formula, and this is available in all technical books. You can find it in the internet as well. Generally, it's just depend on the power of the compressor. Just as you see, just 1 minus pump efficiency, sorry, minus pump efficiency, specific heat of the fluid flow, and fluid density. It's raw, it's not P. Sorry for the, again, for the, it shows like P, but it's raw, it's fluid density. Next step, next things which I would like to discuss, it's specific speed. Why we need specific speed? It's quite nice stuff. It will help you not only designing the pump system, but actually modifying the pump. Let me complete this specific speed stuff, and after this I will go to the question. I think I will not be going far away from the question. And specific speed, why is the specific speed and specific diameter? It came from American Institute, and Europe is just trying to minimize its use as much as possible. If you go to UK, they're using the specific speed, but specific diameter is just they're using very rarely. And what's beauty of the specific speed? And what it indicates? Generally, it indicates the shape of the impeller. If it's a long impeller, it will be creating higher pressure, but flow will be restricted, and specific speed will be much, much smaller. And if you backwards, your specific speed is too high, this means your pump is running in axial flow position as well. And what's the beauty of the specific speed? There is some kind of operation called cutting the impeller. You order the pump and you install the pump, but pump generate too high pressure on the discharge, or just your process conditions changing and you don't need this high pressure, but you need more flow. You cannot provide this. What is being usually done? The impeller circumferentially is being cut, and the length of the passage is just reduced. It's reducing the specific speed, increasing the flow, and reducing the discharge pressure. Nowadays it's being made less and less, but in the past it was just very, very, very often. It has been done very often, especially for refineries. Refineries are just, for example, one standard type of pump was bought, one standard pump impeller was bought, and just what they was doing, they was cutting the impeller for each pump case. Of course, it will not be as good as newly designed pump, but actually as a for short-term solution, or for the cheapest solution, the specific this cutting the impeller can be used, and specific speed, it can be used for this. But actually, specific speed doesn't mean how much you need to cut. It doesn't. It's totally different. This is a representation of your impeller. How would they say? Impeller shape, and also at what range your pump is running. Let's go to the questions, because I might miss something. Brake power is just power provided by motor. BP approved solution, cutting the impeller. Nice question. Okay. Our current standards doesn't mention about this cutting procedure, and mainly in America, it's still used. In Azerbaijan, yes, we have done it once for produced water in one of the products, and actually done by the company who was designing the pump as a very short-term solution. Our standards generally doesn't say anything about this one, and actually this is very, very widely recognized procedure. Generally, what I would like to say, now more companies are just tended to order new impeller or just modify the pump internals, keeping the same casing, but just cartridge, changing cartridge. But again, in some very short duration of time, you can cut the impeller as well. Of course, there is some limitation for the cutting. They can cut for the, some kind of, let's say 10%, 15%. It depends on the impeller. It depends on but not much more than this, because it just will be affecting the pump performance. And actually, this is solution very well investigated, risk assessed, and after this is done. Generally, there is no big problems. And if you see from the top of the curve of the pump is changing, for example, if your pump is just, after the cutting, your impeller curve becomes a little bit inclined, and head is just only the same head only during the dead head condition, and you will not, but flow will be increasing a little bit. Efficiency drops, but actually, and power also drops because just you are producing less power pressure on the discharge. Yes, I think that just cutting the impeller is still approved. Still approved. Next things why specific speed chart can be used. This is just a chart which is used mainly in America. European companies doesn't use this one. Generally, and BP also doesn't use this one, but actually in technical stuff you can find this kind of chart. It's depending what's your specific diameter. It's just diameter of the impeller basically, but actually there is some kind of calculation around this one you see here. And specific speed, suction specific speed, you can choose what type of centrifugal pump you can install. And there is a rule of thumb 500, and actually it's over there as well. If your specific speed below 500, there is no centrifugal pump can be useful for you. It needs to be positive displacement pump. Still, a lot of companies are just violating these kind of things and changing. They're even using the centrifugal pumps for the specific speed lesser than 500 and positive displacement for the specific speed higher than. Don't want to stay on this topic too much. And let's go to positive displacement pump. Positive displacement pump is alternative to centrifugal pumps. And this is a little bit, this is most ancient. They was developed before centrifugal pump. But, and to be honest, they are more robust. The problem with the positive displacement pumps, they are more expensive and they need to be maintained continuously. They are not as robust as centrifugal pump. To be honest, they are not very unreliable as a technical information say. Just for example, if they centrifugal and positive displacement pumps, they compare positive displacement and centrifugal pump reliability. They said just there is big problem, but actually the difference between it's not very big. Positive displacement pump requires exactly slightly higher amount of people and resources to maintain themselves, but actually than if compared with the centrifugal. Previously I stated two main subgroups of the positive displacement pump. Previously I was saying just piston pump, but actually here I give only plunger and diaphragm pump. And for rotary pumps, there is wide range of the pumps, and actually some of them are very. There is gear pumps, lobe pump, vane pumps, progressive pumps, progressive cavity pumps, screw pumps, and so on. And what's the beauty of the positive displacement pump? There is some application which you need use only, which you probably should decide to use positive displacement pump. As there was one question about viscosity, which pump you would prefer for viscosity? For variable viscosity, especially variable viscosity, what I mean under the variable viscosity, for example, Lube-oil system for the pumps, for centrifugal pumps including, they are just using the positive displacement pumps mainly. Because they are operating when the lube oil is stored in one tank, which is exposed to ambient temperature. Temperature of the lube oil is being affected by the ambient temperature. Temperature of the lube oil is being affected by the pump operation. It might be running on high load, low load, and actually lube oil will be affected. Lube oil temperature will be changed. For example, in turbines, there is working oil, not working, mineral oil system, and which is synthetic oil system, mineral oil system, which is synthetic oil system is pumped into the bearing of the turbine itself, and depending on the load of turbine, how much fuel gas and temperature of the synthetic oil is also changing. And because of the changing temperature of the viscosity of the oil also changing. But you need provide constant flow at the same viscosity. If you put the centrifugal pump, the flow from the pump will be quite different, will be changing. Every time when temperature change from the summer, one flow, from the winter, another flow. At high load, it will be different flow. At low flow condition, it will be different. And positive displacement pump usually are used in the variable viscosity service as well. I will explain the effect of viscosity on positive displacement pump performance a little bit later. Another thing, just low shear pumping, especially for the kind of, there is some kind of pumps which especially preferred for low shear pumping. For example, if you're handling produced water or just oil which contains water, for the oil containing water, it's a little bit rare, but actually for water containing oil, it's quite, you don't want to break down the small droplets of oil in the water because you will not be able to separate this oil. You need oil droplets as big as possible. And centrifugal pumps are very good of breaking these small droplets. But there is some kind of positive displacement pump, especially called progressive cavity pump. They don't do anything to these oil droplets, and they're very preferred for this service. Next thing is solid handling capacity. Some kind of pump, for example, screw pumps, gear pumps. There is some erosion between the moving parts, but actually they can handle much more solid loading in a liquid rather than centrifugal. Also, centrifugal pump nowadays can handle up to 50% of solids in a liquid. It's not a big problem, but real limitation is over there 25%. But for the reciprocating, it might be also up to 50% when a liquid is still Newtonian. Next one is multi-phase flow. Progressive centrifugal pumps are very, they are just suffering from if the air ingress or vapor ingress into the pump, the impeller becomes unstable because the impeller rotates in the area. For example, case is half full of liquid and half full of gas. Impeller, when it rotates, it hits the liquid surface, and after this comes out of liquid, and it's 3,000 times in a minute. So it will be becoming unstable. It will be high vibration, and it will be broken down. For multi-phase flow, it's well-known technology is just screw pumps can be used. They're self-priming. They don't need anything. They will pump liquid and gas as good as possible, and even with the solids as well. Another thing, just this is really matter for some cases. For example, in areas with restricted power availability, it's a combination of high pressure, low flow with efficiency demand. Positive displacement pump much more efficient than centrifugal. For example, 90% of efficiency is normal for the positive displacement pump. I know that some of them is just as good as 95%. If it depends on where do you operate this positive displacement pump, they might be as efficient at 95% of efficiency. If you don't want to waste energy, you might go to the positive displacement pump. This is just sometimes, if you in the beginning of the presentation I said just sometimes big positive displacement pump with a bigger flow and lower differential pressure are just produced, and main reason is just efficiency of the pump. This is very rare cases, but they are existing. They do exist. And another thing, just self-priming and inlet conditions. Inlet conditions not very proper, but actual self-priming. Positive displacement are self-priming. They don't need to be primed. They can take all liquid and all gas through it. And as I previously said, just constant flow against variable system pressure. Even it's not only viscosity cannot affect the operation of the pump. Also discharge pressure. In some cases, you need to provide exactly the same amount of liquid despite of the pressure on the discharge. This is very applicable in nuclear power stations when for cooling stuff. Just in some cases, they're using the centrifugal pump, but for example, for emergency stuff, or during the startup, they're using the positive displacement pump. And the last one is one of the main ones is accurate, repeatable measurement. Positive displacement pump will be definitely taking, for example, 1 liter of liquid and pump 1 liter of liquid on discharge. And for example, in some cases, when you need to measure the liquid which you are pumping, the positive displacement pumps are the perfect rather than the centrifugal pumps. For example, chemical dosing pumps. All of them are just positive displacement because you know how much liquid you're pumping, despite of the approach condition on discharge, despite of the approach condition on the suction, it will be pumping the liquid exactly as much as you want. Here I would like to share pump curve, positive displacement pump curve. Let me go a little bit. And as you said, if you remember, pump curve for the centrifugal pump was just going like this, but here is straight line. In reality, it should be ideal. It should be straight line vertically to the flow axis or parallel to the pressure axis. But just because there is some small slip, it means some valves on discharge and suction of the valves, or just gap between the rotor and casing in the screw or gear pump stuff. There is some liquids flowing back to the pump suction side, and actually this is called slip. And slip is as high as the pressure of the pump. At the lower pressure, slip is just negligible. At higher pressure, slip is higher. And actually, in this curve, it's just written, it's indicated as a straight line, but in reality, it's slightly inclined towards the pressure side. And here, just I can show you, and actually, this is the real beauty of the positive displacement pump. Its operations very negligible, affected by the viscosity. In main cases, it's just totally ignored. There is only just pressure drop across the inlet and outlet valves, and there is only losses due to viscosity change. And that's why for the higher viscosity pumps, for the positive displacement are just preferred. And if you see just, for example, if your pump due to viscosity change or just for high viscosity or low viscosity change needs to be, its flow will be negligibly different. On the left side, on her right hand side, you will see that just typical pump curve. It's straight line, and actually, as you see, that just it's given pump speed and flow, which provided by pump, and actually you can choose whatever flow, and it's straight line, it's linear, and the same with the power as well. It's linear. It's one of the main things which, when you are designing the positive displacement pump, is acceleration head. As you know, that just there is some this formula which is required for the NPSH available, and actually there is the main stuff acceleration head. For example, if you will be using exactly the same formula for the centrifugal pump and positive displacement pump, there will be one problem, it's acceleration head. Acceleration head also should be considered when you are calculating NPSH for the positive displacement pump. I think acceleration heads, you should, but actually I will repeat, no problem. Acceleration head generally, positive displacement pump are just pumping one flow and after there's a stop and just taking some liquid from the suction, again pumping the fourth. And during the changing in direction of the flow, whole system is resisting to the flow change. Acceleration is just generally change the resistance of the system to the flow change, not flow change. Let's see what's the pressure. Okay, first could you can positive displacement pump install on the same plant or platform, which is one beneficial. As I said before, your first choice should be centrifugal pump, but actually there is some points which make centrifugal pump useless. For example, if you go to the lube oil system, all lube oil system pumps are just positive displacement because of viscosity. Another thing just you can consider for the pressure. If you are thinking, for example, for pressure, if your discharge pressure is changing, but you need to provide the same flow, you will not be giving the centrifugal pump. Now, on platform, we've got a lot of positive displacement and a lot of centrifugal pumps, and the same on the plant as well. A lot of positive displacement, a lot of any compressors, any pump running with running lube oil. Lube oil is a positive displacement pump. Any glycol pump, MEG pumps are positive. Okay, I would like to give you, I think it might be interesting to you because, for example, we've got 3 pipelines providing liquids to the platforms. One of them MEG, two pipelines. One of them produced water, which is collected on Sangachal terminal. Another one MEG, which is regenerated on the platform. And MEG pump is, and both of them needs to overcome very high pressure head because it needs to be transferred through the pipeline to the platform. Both of them running around the same discharge pressure, 190, 210 bar G, around the same. But MEG pump is a positive displacement because of its viscosity, and water pump is centrifugal. Although there is small flow, high pressure, it's still centrifugal. Mainly when you are designing this pump, just first choice should be centrifugal because they're well known, all operator, and very less problems, very less mistakes you can do with centrifugal pumps. With a positive displacement, if you close the discharge valve inadvertently or something inadvertently, it will be disaster. So a lot of things to consider. It's not very easy, actually. In PD pump, do we have slight discontinuity in flow when compared to centrifugal pump? Yes, I'm going to this one. Yes, flow change and there is some kind of things. I will come to this a little bit later. Mehdi, I think I answered your question. Yeah, okay. And this is acceleration head. I think acceleration head can be easily calculated from the formula. Again, this formula is widely available in internet, in technical books. So main stuff when you are calculating NPSH for the centrifugal pump, for the positive displacement pump, you need to take into account this acceleration head. Rashad, I will be slightly over the time. Is it a problem for you, or there is not a lot of slides remaining, but actually I would like to, is it okay for you?
No, Tarlan Bey, it depends on our speaker. There is no any time restriction.
Okay. I know, I understand it's lunchtime. I know that just this a little bit, but I think I would be very happy if I will share this with you. And I will be very happy if you find this useful or just good. And now I came to the NPSH required, how it's identified. And actually I have been in the tests, and actually I know this from the physical test. Somebody asked me before, and actually I would like to come. Generally, this picture shows how different NPSH required identified for centrifugal test data and reciprocated test data. Generally, pump test is done in a loop. Pump installed in the middle, pumps water from the discharge back to the suction, and there is line connected to the suction tank, but not the recirculation is not done through the tank. It's done through the pump discharge straight to the line and just connected to the suction tank, and suction tank is just providing suction pressure over, suction head over. Why it's done so? Mainly for efficiency calculation, because when it's pumping through the pump, its temperature on the pump discharge and temperature on pump suction is calculated, and on the and energy losses are calculated from the temperature. If it's done through the tank, there will be more dissipation, energy dissipation, and it will be slightly difficult to calculate. Again, some companies doing this one, but actually it's known and actually accepted through the pump, because you are measuring temperature on the straight on the suction and straight on the discharge. So tank should not be affecting, but actually this is common practice, and they don't use the flow through the tank. And during the recycle, they're installing two valves, one of the discharge and another one suction. On the discharge, it's understandable that they're just closing the discharge. On the fully open suction valve, they're closing the discharge valve and checking the pressure and transferring to the head and putting into the curve. But when the suction valve is used, it is used only for NPSH required. Discharge valve fully open, and they start closing the suction valve and see what the head is pump is still generating. And this is just curve on the right hand side for centrifugal type pump. And you see just it's first closing the suction valve, even changing the suction pressure, not closing changing the suction pressure initially doesn't affect the total pump head at all. And then when it came to one point, when the suction head reduction, it's leading to the pump discharge head, total head reduction. At 3 points, they don't want to go further, so 3% of initial head. And this is specified as NPSH required for centrifugal pump. For reciprocating pumps, it's done slightly different. It doesn't say just head, it's under the pressure, because on recycle it will be seeing pressure just only because some energies will not be seeing, just it's depends on how you do this process. But actually for better, I don't remember why they did, but actually they did it under the pressure on the suction. I don't remember why they did. Maybe because of the accuracy of the data, maybe, but I don't remember. And at constant suction pressure, they're doing exactly the same. They start closing the suction valve. And initially, pump capacity is not changing, but later on, capacity is dropped down, but mainly vaporizing the liquid inside the pump. And another thing, just what I would like to mention, just NPSH for the positive displacement pump is more cavitation occurs on the suction valves, cavitation occurs on the pistons, plungers, stuff like this. If it's in screws, then your screws is just totally lost. Cavitation, let's say even 15 minutes of cavitation can destroy your pump totally. Even not 15, it's just 5. 5 minutes is enough to destroy. So NPSH might be very main value for positive displacement pump. I hope I answered to the question how NPSH required is identified for centrifugal pump, which was previously. Again, despite of the centrifugal pump, positive displacement pump doesn't suffer from the NPSH system resistance change. If system resistance curve changing, doesn't matter. Pump will be pumping exactly the same amount of pump. Its performance will be slightly different, but not dramatically different. This is beauty of the positive displacement pump. If you need that, just if resistance curve is changing and your pump, its best case is just. Main thing what you should consider when you're designing is positive displacement pump. The pressure pulsation, as just previously one person mentioned that just pressure pulsation will happen, is very common for the positive displacement pump, yes. Performance and speed. I will be explaining about this performance and speed and overpressure protection. For overpressure protection, for centrifugal pump, you can design the pump head as much as you want. For example, if your system is designed for 10 bar G, you can design the pump with a discharge pressure on the dead head with 9 bar G. There is no problem, and you can be sure that your pump will never go over the design pressure of the system. Positive displacement pump slightly different. They definitely will be overpressure at any cases, and doesn't matter what is the suction pressure, what's the discharge pressure. If you close a discharge valve, if something happens on discharge valve, you will be rupturing everything, starting from the pump seal, starting from the pump discharge lines, everything. And you need to consider overpressure protection for the positive displacement pumps. There was one case when the positive displacement pump was installed for very viscous vacuum residue, which was pumping from the one refinery to another chemical plant. This vacuum residue from the one, I think it was just somewhere in the UK. I don't remember. And positive displacement pump was installed. The vacuum residue was preheated, and actually it was flowing with no problem. But time to time they was pigging this line. And during the pigging, some kind of things stuck in the pipeline, and they ruptured everything because of positive displacement pump increased pressure almost 3 times more than its design pressure. So one of the considerations is overpressure protection. I will come to the performance and speed and pressure pulsations as well. Ideally, you can design the system with a minimal pressure pulsation in a system for the positive displacement pump. Later on, I will just show you. And if, for example, your lines are wide enough, so resistance to the flow change is so small, NPSH acceleration head is so small, so pulsation will be not very great. And for example, again, I'm coming for a lube oil system for the pumps, compressors, and turbines, and they don't have any pulsation because line is too big for the pump delivery. It delivers 2-3 meters cube, 1.5 cubic meters per hour, and line are 4-inch, 6-inch, so pulsation is minimized. Also, the loop is too short, minimize it. But if you put a small bore, you will definitely have the pulsation. Pulsation is mainly depend on how many stages of the pump, not stages, how many heads on the pumps do you have, or just how many screw sections in the screw pumps do you have, or how many teeth section or isolated volume sections in your gear pump have. For simple reciprocating pump, for example, single acting for 100 360 rotation will be just, for example, this flow will be increased, flow will be dropped at the end of the half of rotation, and next rotation, no flow will be forward, and flow will be sucking, pump will be sucking the flow from the section. And this is flow change for the, and this is just change in the flow within the pump. Of course, if you put 2 cylinders, 2 pistons, it will be twice. And if you put 3 cylinders, then your flow fluctuation will be much, much less. But for each stage, it will be exactly the same. If you go further with the 5 plungers, your fluctuation will be even more or less. So ideally, you can minimize your pulsation as much as possible to the negligible case. But any case, anyway, a lot of companies, even with the 5 plunger pumps, with the 6 plunger pumps, with 8 plunger pumps, they're using the pulsationer dampener. There is, again, as I said, just 5 methods of pulsation dampening. If you properly designed lines, if it's big, and your acceleration head, you can reduce the acceleration head as much as possible, your pulsation will be minimal. With the 5 plunger pumps and more plunger pumps, it will be very negligible. But if it's not, for example, metering pump have got only 1 head, so you will be, this is unavoidable. The equipment called bladder or pulsation dampener is usually used. What is it? Is it just metal vessel, small metal vessel, filled with a nitrogen? Or nitrogen is preferred because it's compression constant. Compression constant is just around the same for the very wide range of temperatures and pressures. And nitrogen is preferable. And it's vessel filled with a nitrogen. When your pump starts pumping, and the pressure in the vessel, it depends on how you will calculate it, but actually rule of thumb and just industry-wide technique is just 80% of the pump discharge pressure. For example, your pump discharge pressure is 10 bar G, your bladder, nitrogen in a bladder when the pump is not running should be 8 bar G. When your pump starts, just increasing the pressure till the nitrogen squeezes, and further fluctuation are just taken by nitrogen. Nitrogen is just compresses and discharges, discharges between the strokes and minimize the pulsation. It cannot take fully whole pulsation because it also acts as a pump itself. And usually industry-wide practice is just 5% of initial, its remaining pulsation will be stay 5%. It's from peak to top flow, from the peak, from the low peak to the top peak. It's reduces the dampening the fluctuation in this zone. There is inline damper. It's exactly the same. It's a pipe, rubber pipe within the metal cage, and recharge it with the nitrogen as well. It's the same. Another thing, just hose. This is widely used in mainly in aircraft. They are using for a lot of positive displacement pump, and they are using the hoses, and actually it's efficiently take the pulsation. In some cases, for example, from fire systems, they are also using the hoses, fire on the discharge of the fire pumps. But actually, this is depend on which country you are in, because UK doesn't recognize this kind of things. France, Germany also doesn't recognize hose installation on the fire pump discharge. And last one is resonator. Resonator is the most beautiful stuff. It's just it diverts the fluctuation in resonation into the plates which is installed inside the resonator, and these plates are just reducing. The beauty of the resonator I will tell you a little bit later. But the resonator doesn't very robust, but actually resonator came very recently to the business for the oil pump, for the positive displacement pumping. It used on the compressor, positive displacement compressor, but very how they say, recently it started to be used on the pumping system as well. For example, in BP, we are using resonator on Chardonnay's 2, very new system, where the resonator installed on the lean mech and the lean mech pumps, which is pumping mech to the platform and pumping mech to the plant as well. This is quite, I wouldn't say it's just state-of-the-art technique, it's just quite very novel, but actually they never used on, they previously very rarely was used in the pumping system, but now they're more and more. And there is some rumors, not rumors, there is some dislikes by some companies, and based on the things that just resonator plates can be broken inside the resonator with no notice, but another companies just, especially BP, are just prefer them and using them as well. I would like to go to the question. After this, I will go further. Examples which cause a pulsation. Cause of pulsation is just, as I understand, is just movement of the plunger inside the cylinder. When it's sucking the liquid from the suction, there is no forward flow. When it's starting the discharging the liquid to the discharge, there is no flow in the suction. And both sides are just have a pulsation, and pulsation which is leading to the vibration mostly. And this is general examples. The same with a screw pump. For example, screw is just 2 screws. Some liquid trapped between the 2 screws is pumped forward. And when the first portion of the screw, one portion of the liquid trapped between the screw sections arrives at discharge, it just creates some flow, then it stops. Another portion of the liquid, and actually this is just how they say, this is liquid provision in the small portion, in the small batches, creates a pulsation in the system. I'm sorry if I couldn't explain it much better than this, but actually thank you very much for asking this question, because I found something very informative stuff just to say about this one. Bladders. Bladders are usually installed on the pump, suction, and discharge. As I said just previously, because it's just two places where the pulsation happens, on the suction line and discharge line. Some companies don't worry about the suction line because it's running on the low, and they don't put the bladder, but actually, rule of thumb, the best practice to put bladders on the suction, on discharge. And the same with the resonator, the same with the hose. Vibration and pulsation can be increased if your suction and discharge valves are passing. In this case, your vibration will be higher because, for example, if your suction valve is passing and during the discharge of the liquid, you are not only stopping the liquid from the suction, you are putting the flow from the piston back to the suction line as well. So this increasing the vibration and increasing the pulsation because flow physically changing as well. Okay, I will just check. Okay. Okay, good. Now I would like to just physical, it's all pulsation dampener. It just doesn't matter which one of them. I would, but actually this formula given only for pulsation dampeners, which is using the nitrogen, this inline and bladder type, not resonator and hose type. Oops. And if you see, for example, if without any pulsation dampener, your pulsation is big. As soon as you put pulsation damper, your pulsation still there, but actually they are much, much smaller. There is some kind of explanations given here. It's quite nice, triplex pumps curves. It just when the two pistons poles is just coincide inside, just pulsation is slightly higher, and the same for the section. And this is a formula to calculate when you're just designing the pulsation dampener. You are just need to. Why I'm giving this? Because the procedures are just very wide, and actually it's only for show, to show how it's done. And first you need to identify what will be your pulsation damper volume. And for this one, you need what your pump stroke, and what is the dampener pre-charge relation to the, for example, to the discharge pressure. It's 80% of the discharge pressure, 70%. And actually, this is poorly what you want. Some people are just, there is no strict rules. BP procedure says 0.8, but actually it's not so strict. It's just something like suggestion. Generally, people choosing the 80% because it came from the experience, for a long time experience, and level of dumping. And level of dumping, and what's from the peak to peak, this peak, flow difference, how much you would like to reduce the flow difference. And usually it's 5%, but actually some person can go to 1%, and some person say just 5% is just too big. I can survive with the 10%, and this is really depend on the current BP procedure, 5% and 80% of this one. And type pump constant, it's just standard, all standards. This is for the number of plungers. For example, one plunger have got, I don't remember, I know that triple X have got, I think 7 constant. They're also widely available in internet, in the standard. You can find this in all standards. It's available, and you can use these figures. And actually, this changing not from the, how they say, the mainly it's changing by number of the pistons. For the one piston, it's just something like 1.8, I don't remember, 1.5. For 3 pistons of 7, 5, it's even more, I don't remember. Something like this. And you can design. And now I would like to go back to the resonator. And there is one negative stuff about bladders and one positive stuff for the resonator. As you see here, it dampener pre-charge temperature pressure, and dampener pre-charge pressure depend on the pump discharge pressure. When you're changing the pressure, discharge pressure, your dampener pre-charge pressure becomes obsolete. It doesn't need it will not. You can design the system, this bladder, only for one pressure, for one particular, plus minus 10%. Okay, it can be changed. It will be survive in some area. But if you are below of this pressure or higher than this pressure, you need to design new bladder. And for the changing resistant curve pumps, it's quite important. Whereas or just changing speed pumps, it's just changing the volume pumps, it's just disaster. But for resonator doesn't have this negative effect. Resonator can help you with the dampening of the pulsation at any pressure, at any flows, at any stuff. They're a little bit expensive, but actually resonator, the beauty of the resonator, they can work on wide range of this stuff, wide range of the operating conditions. I would like to answer to the question, and after this go. Oh, nice question, very nice question. Pressure surge and pressure pulsation is totally different. Yes, they are in nature might be similar. In nature, yes. Actually, pressure surge is just, for pressure surges, we're also using the dampeners. And for pressure surges, we're also using the resonators, hoses, and exactly the same. And in nature, it's just, yes, it's just changing in a flow direction. But pressure surges is just very, very, very severe, much severe. Where this one is just not as bad as it. I'm happy. I will be happy if I answered your question. I don't. This is quite rare question. I never faced with this question, with questions like this. Another thing, just pump efficiency. Pump efficiency depends on the valves, suction valves and discharge valves. If discharge valves, suction valves are perfectly operated, it will be dramatically reduce the pulsation. And it depends as high as your pump efficiency, as good as your system in terms of pulsation. For example, in table, I've given average efficiency of the pump. For example, internal gear 90, 85. It's vane, radial piston, bent axis piston, axial piston. It's just 90, 91, 92%, and actually they are just less. For example, I know that for radial piston, it's the same piston type, but actually the pistons, I don't know how to explain. If you have seen the airplanes of World War I, they was installed with the radial motors, and actual radial motors in front of the planes. And these radial piston pumps are just exactly the same copy of this kind of motors. And actually, in radial piston, nobody puts any, also it's just positive displacement, also it's the reciprocating by means, but actually nobody puts any pulsation dampeners. Not because of its type, it's mainly because of the number of the pistons. Number of pistons so big, it might be 16 pistons, so fluctuations are really small. But generally what I wanted to show here, just as much as your efficiency of the pump is higher, pulsation is less. Pump control. How we are controlling the positive displacement pump? There is three main types of, yes, there is four main types. Actually, I will speak of speed control. Speed control is just can be done in two cases. One of them in terms of the centrifugal pumps, by changing the frequency of the motor and changing the speed of the pump. Do you have any questions before going? No, okay. And when you are changing the speed of motor, your speed of the pump is changing. But again, be aware of your bladders. Bladders needs to be, every time when you are changing the bladders, needs to be redesigned, let's say, rechecked. Another thing, just speed, how change, because majority, mainly 99% of all positive displacement pump between motor and pump, there is a belt between them. And you can easily change the belt pulleys and change the pressure speed ratio between motor and pump. And you can change the speed of the pump at any time would you like. Another just method of controlling is just flow back or spill back line, bypass line, recycle line, how you would like to call it. In this case, it just shows it controls the flow on the discharge, but actually it can be any other process parameters. It can be level in the column or tank. It can be pressure on the discharge or pressure in the system where it's pumping. It can be any of them. And actually, this is widely, and actually, this is the most reliable method. The only negative things, when your discharge head is too high, the risk cavitation usually happens around this valve. And you need to consider this one generally for the design of this valve and design of your pump system. Another thing just very widely used in the chemical injection pump is the stroke control. The stroke is just the length of the length, how far this piston is goes inside in the how we call this cylinder. Okay, how far it goes in cylinder. By changing this one, you can just change the flow through the pump. Again, your dampener, it needs to be redesigned again. Usually we don't do this because pressure is not changing, but actually, this might be one of the problems why rupture in this metering pumps or membranes or kind of things. It's because it operates in wide range of pressures, and your dampener is designed only for one pressure only. And what is specialized control technique? Each company provides very different type of technique. One of them is just, it might be different. For example, for the vane type, the position of the rotor inside the cylinder can be changed, and the volume between the vanes and the casing can be changed and change the volume. The same with a radial piston pump or just axial piston pump. The center line is not installed in the main cage or center, it's just under the slight different and actually different position. And actually by changing from towards center to the peripheral, you can change the pump performance. That's it for the positive displacement pump. And actually I would like to give very short information about jet pumps. It's only 4 slides. Jet pumps, I've got some kind of negative stuff. It's one of the greatest pumps. It have got very big advantage. It's the most cheapest pumps, and actually you can buy $150 on jet pump. It have got no moving part. It can work for the maintenance free for the length of the life, 50 years. There's no change, there's no maintenance. It can be installed whenever you want. Whenever it doesn't cavitate, it doesn't need special NPSH requirement, doesn't need anything. Very robust pump. And to put in operations, there is no special procedure, just open valve and put flow through the pump, nothing. And materials of construction, because in terms of centrifugal and positive displacement, because of the, for example, in positive displacement, there is continuous movement inside, how I would say, just friction between 2 units. So some materials are not appropriate for the positive displacement pump. Some materials not appropriate for the centrifugal pumps, for example. But for the jet pumps, any material can be used, especially these kind of things like ceramic. They can be used for the jet pumps, and this is greatest advantage of jet pumps. And you will find very enormous amount of cases when the jet pumps are installed. Some companies even using the jet pumps as a booster pump for the big for big centrifugal pumps. And as a motivate fluid, they're using the flow of the recycle flow. And by modulating the recycle flow, they just can adjust the NPSH on the main oil pump suction. This is one of them. There is enormous amount of cases when the jet pump used. I cannot even remember. Another thing, just very, is it here? No, it's not. It's not an actual, another beauty of jet pumps, it can use even dry solids. If you remember, I said just the centrifugal pumps are good if the solids content in a liquid is around 25%. It can be working up to 50%, but some consideration should be taken into account. For the positive displacement, it's something like 50%. For the jet pump, it can even transfer the solids fully dry, 100% solids with a liquid as a modified fluid. It's, of course, it's not coming into the area where the pumps are used, but actually, for example, if your liquid contains 90% of solids, it will be pump, and you can use a jet pump. And jet pump usually it's just venturi tube used for mixing, solid handling, waste energy. It's very nice for the waste energy use. Another thing, just two last one, I would like mass transfer and heat transfer. There more and more are used for heat transfer and mass transfer. For example, in glycol contactors, the glycol is taken in some design. Glycol is taken from the bottom of cone of contactor and recycled back to the cone, whereas a triethylene glycol and gas, which is coming in, is mixed and pumped back to the cone and reducing water content of the gas. They're very nice for the mass transfer, and actually it's not only one case, there is enormous of another cases where the even salt is dissolved from, for example, from the natrium, paraffinic acids, natrium salts of paraffinic acids from the diesel is just dissolved in the water. They can use this one, and actually they're very widely used. The same, it's used for the heat transfer as well, when the one gas, not liquid is filled, provided some heat to another liquid to vaporize or just drop down some liquids. It's more related for the gas, but actually it can be used for the liquid as well. Before going to another slide, I would like to answer to the question which is here. Okay, I will tell you. No, actually it's used. Even on offshore platform and refineries, they're very widely used. You will find a lot of them. They're not just only so obvious as a centrifugal and process displacement, but they are used. And the main now answer to your question, it's efficiency. These pumps are very low efficient. Their efficiency very hardly goes above 25, 26%. That's main stopper for this kind of pumps. Generally, you are using the power of another stream, and stream needs to be conditioned before use. And its efficiency primarily depends how much head of the initial liquid and what's the head of the second liquid, and also what's the proportional rate between primary liquid and secondary liquids as well. And pump control of jet pump control, it's also very easy. There is no various methods, and actually this is just only sophistication of the controls. Usually it's controls only by liquid which is enters to the primary liquid. Sometimes the secondary liquid also is controlled, and sometimes it's only controlled by secondary liquid. Sometimes it's controlled by bypass. Sometimes it's just throttle position change. There is internal, there is throttle. And by moving this throttle towards left and right, you can change the you can change the pump performance a little bit. This is too sophisticated method, and actually this is used for mainly for gases rather than for pumps, but for pumps also is used. And vortex strength control, it's just the same liquid, which secondary liquid is not given straight away to the center. It's given in tangential, sorry. Primary liquid, not given in straight in front, it's given tangential, making the vortex inside and increasing the efficiency generally, but actually this is also very rare type of control and not many used. That's it, gents, ladies, gents, that's it. I shared all what I knew about pump and control. There is some kind of another things as well, but actually we are limited in time, and actually I think I provided quite an enormous amount of information and threads.
Yeah, definitely. Thank you very much, Tarlan Bey. It wasn't just a technical session, it was like a masterclass for us. Thank you very much for sharing your invaluable knowledge. And dear participants, thank you so much for joining us today. and we are looking forward to seeing you in upcoming events.
But actually, if you want to ask some questions online, I'm available. It's up to you.
Yeah, I would like to ask a question, but I don't want to hold anyone on the line.
Yes, go ahead. I will try to answer. I'm not promising that I will answer, but actually I will try.
Yeah, okay. So if anyone wants to leave, I don't want to, anyway. But regarding to the question MPSH required, around 20, slide 20, I guess. Can you come to that again? 24, I guess.
20, just let's go.
No, above.
22,
Yeah,
I think.
22, yeah. The thing is that I can't find so many information on the internet and so on regarding to the MPSH required, how experimentally to get MPSH required. You said that the pump inlet and outlet, we have a valve. For the pump characteristic curve, we gradually regulate the discharge curve, right?
Yes.
But for the MPSH curve, you said that manufacturer was gradually regulating the suction valve.
Yes. For example,
right?
discharge valve is fully open and
Discharge
it generates.
So here, the straight line, till some point we have a straight line, nothing changing the head, right? If we gradually close. So this head, what is this head correspond? Because it's the head basically at the beginning, you fully open the inlet and outlet valve, right? So it means that its pump will work almost in the operating rated head, right? This should be corresponding to the rated head.
Let me explain. For example, discharge valve is open, suction valve is open. It's generating some head.
Yeah. So this head is a rated head, right? Like generally.
It's total head. Just let's go through the curve. It's total head. Let's say head.
Okay.
Then.
So then you said that we start gradually closing the suction valve, and we see that till some.
And actually measuring it's not only on valve. We're measuring as a suction head. We're reducing the suction head. We're not just closing. We're closing, for example, it was just 1 meter head. We're just closing to get 0.8 meter head.
At the suction?
Yes.
So this
discharge head drops, but actually drops exactly the same like suction head dropped. For example, if 2 meter drop on suction, discharge also 0.2. That means the line is straight.
So this is nothing. This is nothing to do with the pump head, right? This straight line. This is just a suction head.
No. It's which curve you mean? Curve with the pump head.
Pump head.
Yes.
So then we start regulating. Then the head curve goes down, right? So
yes.
And this is our MPSH.
Do you understand why it goes down? Do you understand why it goes down?
After a certain point.
Yes.
I can predict that when you close.
Go ahead. When you're closing the valve, liquid starts generating some vapors. It's not enough because volume of the suction in the suction is not enough to replenish the volume on the discharge. That's why, in order to replenish this volume, liquid start generate gases, vapors. And when it comes to the total head, 3% lower than the initial achieved head, they stop this kind of things and they said just, okay, this is your MPSH requirement. And this is depend on the company. For example, Sulzer and majority, 90% of the companies are using 3% of margin. There is some companies which are using the 5% of margin. Did you understand that? Is it my explanation good?
That the explanation is really good. I understand that after decreasing the pressure, we will have a bubbles forming, and then it will lead to cavitation. But always didn't understand on the pump curves that MPSH curve goes with the different flow rates. They have a MPSH curve, right? Because here we have total head versus suction head.
Yes.
But I mean, when we have a pump,
I see your point. I see your point.
yeah, this whole graph. How do they get
Yes.
every time that? This is kind of tricky.
Yes, yes. I see your point. Sorry. I didn't catch from first time. Yes, okay, again, this test done not only for one full open case on the discharge. It's done for several cases as well.
Mm-hmm.
So for fully open valve, later on they just closing the valve, getting the discharge head slightly higher, and do exactly the same test and see the exact same point and putting the point in your curve as well.
Then they are putting all of these points on the graph, and that they get MPSH. Yeah, yeah.
Usually 10 points. Yes.
Yeah. Understand. That's good. Thanks.
Yeah. Okay. No problem.
Is there any additional questions? I think no. Then thank you everyone. Thank you very much for joining us, and thank you Tarlan Bey again for sharing your knowledge with us.
Yeah. Okay. I hope it was useful and it was interesting. I really hope that it was just useful.
It was very much. Thank you very much.
Okay.